Alright, let's go over chemical reaction rates, also known as kinetics. The collision theory. When reactive molecules collide, they might be able to form new products. They must have enough kinetic energy, so energy in motion, and they must collide with the correct geometry. This is essential. So these two things, A and B, are must-knows for our exam. For an effective collision to occur, the reactant molecules must be oriented correctly to facilitate the breaking and forming of bonds and the rearrangement of atoms that result in the formation of product molecules. The rate at which this happens is the amount of reactants changing per unit time. Amounts of reactants changing per unit time. Alright, energy diagrams. Activation energy. Activation energy is the amount of energy needed to cause a reaction to happen. So you see here are reactants, and you see here are products, and you can see here the activation energy is going to be from here to here. And it tells us that we need this much amount of energy in order to actually start the equation and change from our reactants to our products. All right. Activated complex. Activated complex. This is the moment when all the atoms are together before the new products form. So unlike the activation energy, the activated complex is just the tip top, the way top of the line you see here. So on the arrow, this right there is the activated complex. Alright, so let's go over a practice problem using this knowledge. So we can figure out a lot of information from this graph alone, and we're told that the energy of the reactants is 30, the activated complex energy is 120, and the energy of the products is 50. So using this information, we can figure out all of these 8 questions. So we'll start with the energy of the product. So the product is here, and it tells us that the energy is 50. All right. Same for the reactants. The energy of the reactants is given is 30. What is delta H? If you remember back to our previous units, delta H is going to be final minus initial. So if we take, since we're moving from reactants to products, the product is going to be the final, and this reactant side is going to be the initial. So 50 minus 30 equals 20. So our delta H is going to be 20. And if we look at the graph, we can determine whether this is an exothermic, or endothermic. Exothermic is when heat exits the system, so the reactant side will have a greater energy than the product. And endothermic is where the heat enters the system, so the reactant side will have the greater energy, or reactants will have less energy compared to the product side. So based on this information, we can tell the reactant side started with the 30 energy, and the product side ended with 50 energy. So we gained 20 energy. So this graph is going to be endothermic. Endothermic. You could also have realized this by looking at your delta H value. Our delta H value was positive. So therefore, we know that the graph and the reaction is going to be an endothermic reaction. All right. The energy of the activated complex, once again, the way tip top of the graph right there, is going to be given to us, 120. The activation energy is from this point from the reactants to the tip top. So that is going to be the activation energy. We're going to call that AE. AE. And if we look here, we have 120 at the top and we have 30 at the bottom. So 120 minus 30 is going to be 90. So our activation energy is 90. All right. Reverse delta H is basically telling us to flip the equation or the graph. So if our given graph here was looking like this, our reverse would be starting with the products going to the reactants. So all reactions in chemistry are reversible. So we know that we're going to be starting with our products and then converting that to our reactants. So what we're going to do is consider the products. Products is going to be the reactants this time, and then our reactants is going to be the products. So all we're doing is switching. So that is how it will look. And we have 120 on top still, and we will have the reactants 50, and products, prod 30. That is our new graph. So if you look here, the reverse delta H is going to be calculated the same, final minus initial. In this case, our product is 30, so that's our final, and our reactants is 50, that is our initial, since we're going from reactants to our products. So final minus initial, 30 minus 50 is going to give us negative 20. So our reverse delta H is negative 20. Reverse activation energy is going to be calculated similar to how we calculated the activation energy of our original graph. So we're going to look here, and our activation energy is going to be right there. So AE. Okay. So now we take a look. The activated complex is still 120, and the reactant side this time is 50. So when we take 120 minus 50, we're going to get 70, and therefore our reverse activation energy is 70. And one key thing to note is that all we do for reverse delta H and reverse activation energy is we're just going to flip graph. So we're considering reactants to be our products and products to be our reactants. So I'll show that here. All right, let's take a look at our second example. All right, same deal here. We're given 8 things to find, and we are given this graph here. So let's take a look. We're given with reactant energy 70 to start with, our activated complex energy is 150, and the product side energy is going to be 20. So the product side energy is going to be 20, as given. The energy of the reactants, also given, is going to be 70. And our delta H is going to be final minus initial. Our final value is product side, and our initial value is reactant side. 20 minus 70 equals negative 50. Our delta H is negative 50. And therefore, since we know that a negative delta H value correlates to an exothermic reaction, we know this is exothermic. You could have also determined this by looking at the graph. You're starting with 70, but you're ending with 20 energy. So you're losing energy. You have more energy in the reactant side than the product side. So therefore, heat is released in the reaction, and it is exothermic. The energy of the activated complex is given 150. The activation energy is from our reactants points right here to the tippy top of the graph, which is 150. So 150 minus 70 is going to be 80. So our activation energy is 80. All right. For our reverse delta H, we were taught that all we do is flip the graph. So starting with our product side, it's going to look like that. It's a crude drawing, but it gets the job done. So we're going to have our new reactant side and our new product side, and our activated complex is going to be the same. and our reactant side is going to be now 20. Our product side is now 70. All we're doing in this process is getting our reactant sides and moving it over and flipping it. Alright, so now we can calculate delta H reverse. So now this is our final, 70 is our final, and this is our initial, 20 is our initial. So final, 70, minus initial, 20, is going to give us 50. So our new delta reverse H is 50. Reverse activation energy is calculated the same way we calculated in the regular. So from 150, our activated complex, to the reactant. So 150 minus 20 is going to be 130, and that is our activation energy reverse, 130. All right, activation energy. So activation energy is always looked at on the highest peak in multi-step equations. So if you look at this graph, it's kind of small, but we have one curve. So the highest curve is going to be the activation energy. But for these, let's take a look at the last one here. We have many curves. In this, we always take a look at the highest curve. This right here is going to be the activation energy. No matter how many curves you have, it's always going to be the highest curve. So take a look at number 3 here, and this is going to be the most obvious. So if we have this smaller curve here and a bigger curve here, we're always going to take into account the biggest curve, which is going to be our activation energy. All right, let's talk about factors affecting reaction rates. So there's 4 factors that affect reaction rates, and you need to know all of these. The first one is going to be temperature. Temperature. Increasing the temperature increases the number and energy of collisions. So the more temperature you have, the faster the particles will move. Number 2, the second one is going to be concentration. Concentration. Increasing the number of reactant particles increases the frequency of collisions. So increasing the number of reactant particles increases the frequency. So this image depicts this. Um, uh, the low concentration of those molecules compared to the high concentration. So more reaction can take place with more concentration. The third one is particle size. Particle size. Decreasing the particle size gives more opportunities for reactions to take place due to increased surface area. So if we take a look at this, say we have a uh, um, some particle, let's call it like salt or something, right? We have one big block of salt versus many small blocks of salt, right? We're going to obviously have more surface area compared to one big one than many of these small ones. Say we have 100 of these compared to just one big block, right? Then it's going to have more surface area. Therefore, the the reaction will be faster because more of the solute, say the salt we're putting in, can touch with the reacting the solution. So, if particle size goes down, surface area goes up in response. So the lesser the particle size, the more surface area, and therefore the faster the reaction will occur. The fourth one is catalysts. Catalysts are the purpose of these is to lower the activation energy, and this image right below shows this. So this blue sector here shows the activation energy required to start the reaction without the catalyst. But this red line here shows the energy required, activation energy required to start the reaction with a catalyst. So it's clearly decreased much, decreased a lot. So a catalyst will lower the activation energy, and the lower the activation energy, the faster the reaction will happen because it'll take a shorter amount of time to attain the energy required to start the reaction compared to when a reaction occurs without a catalyst. And that is it for notes, day one.